So today we're going to be talking about two super groovy concepts that go along with linear combinations, span and linear independence. But first, what is a linear combination? So if we have some set of vectors here, a linear combination is if we take a certain amount of v1, let's call it c1, and then we're going to add it to a certain amount of v2. And then we're going to add it to a certain amount of all these other vectors, all the way up until we have a certain amount of our last vector. So we can just take each of these vectors as a building block and take a certain amount of them and add them all together, and this will be a linear combination. So then, our first concept of the day is span. And what's span? Our span is So our span is defined as the set of all linear combinations of a set of vectors. So you can kind of think of it like this. If we kind of think of our set as a set of Legos that we just got, all the things that we can build is like our span of those Legos. So we have a certain amount of this type of piece, certain amount of this type of piece, and we can combine them in any way to create something new. So we can take from this set here and we can create anything from these sets, and that's going to be our span. Our span is all the different masterpieces we can create using these vectors as building blocks. So cool. So let's look at a specific example of that. So for looking at some set B here, with the vectors of R2 as -1, 1, 2, 1, and -1, -2, what is our span of B? So it's the set of all linear combinations of these three vectors. So our span of B is equal to the set of C1 times, big one, so we're going to have C1, -1, 1 building blocks. We're going to add that to some number of 2, 1 building blocks and add it to our last number of our last vector, or C3, -1, -2 building blocks. So now we have this span of B, and let's see what we can create. So if we want to take maybe 3 of our C1 of our first vector, we want to take 2 of our second vector and just 1 of our third vector, what do we get? So that means that we're going to have 3 times our first vector. We're adding it to 2 times our second vector. And then we're just adding it to our third vector. And what is this going to give us? So we have 3 times our first vector, which is going to be a -3, 3. And we're adding it to 2 times our second vector, which is now going to be 4, 2. And we're adding that to our third vector, right there, like that. So then this is going to be equal to -3 plus 4 minus 1, which is a 0. And then 3 plus 2 minus 2, which is just 3. So we have just created a whole new vector, 0, 3, using these 3 vectors as building blocks. So this here is in our span of B, because it can be written as a linear combination of the vectors of B. Okay, so now if we wanted to find a specific value in our span, how can we do that? So let's say we want to create 10, 2. We want to construct it using these 3 vectors. So in order for 10, 2 to be in our span, or to be constructed of these 3 vectors, it has to be equal to some constant times our first vector, plus some constant times our second vector, plus some constant times our last vector, which means that we have to be able to write 10, 2 as some linear combination of these 3 vectors. So this will give us a linear system of equations of. So now we can form an augmented matrix from this information of -1, 1, 2, 1, -1, -2, and we're going to augment it with 10, 2. So we go through and do row operations. To reduce this side down to row echelon form, we'll solve the mystery as to what C1, C2, and C3 we can use to construct this vector. So when we reduce it down to reduced row echelon form here, we will see that C1 minus C3 is equal to -2, and C2 minus C3 is equal to 4. So we have C1 and C2 as our pivot variables, and C3 is our free variable, so we can choose any value of C1 or C3, so we can choose any value of C3 in order to find our 10-2. We see that C1 is going to be equal to -2 plus C3, and C2 is equal to 4 plus C3. So since C3 is our free variable, we can choose any value to plug in this. Let's just let it be equal to 1, which means that C1 is going to be equal to -1, and C2 is equal to 5. So now let's see if we can use this information to find our 10-2. So we know that -1 times our first vector plus 5 times our second vector plus 1 times our third vector should give us our 10-2. So what does it give us? We have -1 times our first vector is going to give us 1, -1. 5 times our second vector is 10, 5. And then 1 times our last vector is going to be -1, -2. So what is this equal to? We have 1 plus 10 minus 1 is 10. And -1 plus 5 minus 2 is 2. So voila, we have constructed 10-2 as a linear combination of the 3 vectors in B. So that means that 10-2 is indeed in our span of B. Wow, groovy. So now we have a method to find any vector in R2 using these 3 vectors as building blocks. So as we know that our span of B is equal to all the linear combinations of a set of vectors, we know that first of all, this set is closed under addition and multiplication because all of the linear combinations are in the span of B because that's how it's defined. That means that any span of any set of vectors is going to be a subspace of the vector space that the vectors belong to. So in this example, span of B is a subspace of R2. Whoa, wild. So now let's look at something super important, and that's called linear independence. So linear independence. This super cool topic can be defined as this. So a set is linearly independent if and only if we can take a linear combination of those vectors, set it equal to the 0 vector, and the only solution be all of the values of C are equal to 0. So this is kind of a lot of like mathematical mumbo jumbo. So let's just think about this. So we have this equation here. If we subtract a Ci times some vector Vi from the left side, we're going to end up with this. So then if we divide both sides by -Ci, we're going to end up with something like this. That means that we can write this vector, whatever vector it is, it can be any one from the left side, as a linear combination of the other vectors in our set. But if we had all of these C values equal to 0, we would just have the 0 vector on one side and the 0 vector on the other side. So that's why we call this linear independence, because if not all these C values are equal to 0, this or any vector in here is going to be dependent on the values of the other vectors. So it's linearly independent if each of them stand on their own and you can't write them as a linear combination of the other ones. So now using this idea, let's kind of put it into a little bit more concrete terms by looking at an example. So we're going to be looking at B once more. So we have this set here of vectors in R2. We're going to see if this is linearly independent. So remember, by our definition of linear independence, if we have some linear combination of these three vectors, and we have that equal to the 0 vector, that means that all of these values of C have to be equal to 0 in order for this set to be linearly independent. So that means we have this system of linear equations. So right before, we already calculated our reduced row echelon form of the augmented matrix corresponding to this linear system. So let's recall that. So from our reduced row echelon form of this augmented matrix, we will see that C1 minus C3 is equal to 0, or in other words, C1 is equal to C3, and C2 minus C3 is equal to 0, or in other words, C2 is also equal to C3. So remember, C3 is our magical free variable, so we can choose any value of C3 and plug it in here. So let's see, maybe let's just let C3 be equal to 2. What's going to happen then? So if we let C3 be equal to 0, or equal to 2, so if we let C3 be equal to 2, we're going to end up with this. And now what's this sum? So you have negative 2 plus 4 minus 2, which is going to be a 0. And then we have 2 plus 2 minus 4, which is also going to be equal to 0. So we have just constructed our 0 vector. However, these values of C1, C2, and 3 are not equal to 0. So no way Jose is B linearly independent, because it violates our definition of linear independence. So this also means that we can take any one of these vectors in B and write it as a linear combination of the other vectors. So B, you are not linearly independent. In fact, you're linearly dependent. So let's look at a set of 2 vectors. So now we're going to look at this set C that has 2 vectors of R3 in it. So if we look at this, is this set linearly independent? Let's see if we can find some value of C1 times our vector 1, 2, 3. That's equal to 3, 6, 9. Well, you're looking at it, you're probably like, well, yeah, obviously. If we let C1 be 3, then we have 3 times 1 is equal to 3, 3 times 2 is equal to 6, and 3 times 3 is equal to 9. So we can write this vector 3, 6, 9 as a linear combination of our vector 1, 2, 3. So the set is linearly dependent. So can we find a set of 2 vectors that's linearly independent? Well, yeah, let's think about this. C star is linearly independent. So if we were to take some linear combination of these 2 vectors and set it equal to the 0 vector, both of the coefficients on these 2 vectors is going to have to be equal to 0. Okay, so now see if we can go even smaller. Can we have one vector that's linearly independent? We'll see. So if we have some set here E that consists of only one vector, and this vector is from R4, let's use our definition of linear independence to see if this set here is linearly independent. So that means that if we take a linear combination of this vector, and we're going to set it equal to the 0 vector, what value of C1 will make this true? Well, there's only one solution, and that means that C1 has to be equal to 0, because 7 times something is only ever equal to 0 when that something is 0. So that means that this set here is linearly independent. So does that mean that any set of only one vector is linearly independent? No. I know, that's kind of like, whoa, wait, what? Well, let's consider this. If we take our 0 vector, we're going to multiply by some constant and set it equal to the 0 vector. Any constant, though, that we multiply the 0 vector by is going to give us the 0 vector. So we can choose any value of C1. So we can choose 894. And that's still going to make this equation true, which means that we have a solution for this equation that's not 0, which means that the set of just the 0 vector is linearly dependent, which is kind of weird, but it's true. So we've just learned some really important topics related to linear combinations, so stay tuned in the next video where we make a beautiful concoction of these two ideas. See you next time.